Hello and welcome to the new session of new video, how to read a character table part 1. Actually, we have described the methods of constructing character table in various videos earlier also. But I would suggest you to go through this video as it has some information that collectively is very important for those who are the beginner in this field and those who are the experts in this field. For both of them, this has a worth looking video. So let's go for our new session, that's how to read a character table, and I'm your instructor Saurabh Bhaktibodh. I believe that numbers also have characters, and in the character table these numbers have to be decoded. But then from very basic and fundamental question that comes in your mind is, what is a character table, isn't it? And the chemistry students learn to develop a character table with or without using complex mathematical functions. But the question is, what is this character table? Ultimately, we have to understand and how to read or understand it. That's the question, of course. And is it as simple or complex as to read in horoscope? Say, for example, the Pandits of India, the astrologers and Jyotishis, they understand their tables quite well. Is it that easy to understand the character table? And we are familiar with our character table. It looks like an horoscope also. At some point of time, you see the point group of the molecule, then the symmetry elements, then the symmetry labels talking about irreducible representations, then there are characters, then numbers, then there are some basis functions, etc. So what it is and how is that important? And if we understand the components of character table, how to draw inferences for chemistry applications? I don't know. What does it mean? A character table, what the hell it is? Well, yes, this is how a mind gets occupied when you look about a character table. We know that the molecules that have been classified into various symmetry properties, like males and females we have. Similarly, molecules have peculiar characteristic point groups, like for water it is C2V character table, and for other one it is a tetrahedral molecule. And we understand that if we talk about water molecule, it has a peculiar C2 point group that has 4 components, 4 symmetry elements, including identity, as E, identity, as C2, sigma V, and sigma V dash are the 4 symmetry elements of this point group. Then each symmetry operation can be represented in the form of matrix corresponding to a Cartesian coordinate system. Thus, we have a set of matrices now. So, matrices have actually the information that is in a coded form when a particular operation is carried out, and this coding would be very important to generate informations. These matrices can be decomposed to smaller dimensions using a method called similarity transformation technique. So matrices can be decomposed into smaller components using one simple mathematical operation, that is similarity transformation. And once if we are able to do it, then those matrices which can be decomposed are reducible matrices, while those which cannot be further decomposed are the irreducible representations. Look at here. Here, let us believe that this is a 3x3 unit matrix, and if by some means, that is so-called a similarity transformation method that we have described in earlier videos as well, if it is possible to decompose into a smaller dimension and further into a one dimension, so the 3 dimension can be decomposed to a 2 dimension and can be 1 dimension respectively, then these matrices are reducible matrices. However, this matrix, which has only one component, cannot be further decomposed, so that is known as the irreducible representations. So a 3D can transform into 2D and further by 1. This kind of transformation is mathematically possible only using some techniques. And that technique is similarity transformation, as I have described. See, for example, there were 3 by 3 rows and 3 column matrix, and if it is possible to just block diagonalize, so this is actually a 2 by 2 and 1 unit matrix. So this similarity transformation is such that C inverse AC is equal to B, and C inverse 0, of course, identity. But then these operations give a new result. So as we have seen that a matrix that cannot be further reduced or further decomposed is irreducible representation. Is it the important component? Yes, it is the most important thing. They are of fundamental importance, and they can be of 1 dimension, 2 dimension, 3 dimension, etc. And this actually determines the dimension of matrix, which cannot be 0. You cannot have a 0 order matrix, and you cannot have a fractional order matrix as well. You cannot have a matrix of order 1.2. So it is either 1D, 2D, or 3D, etc. and they can be obtained by matrix manipulation. Now, how we have a basis for character table? Because a character table is a collection of characters of irreducible representations of a particular point group or a particular point group. Now, the next point that needs to be understood is then what is character? And the answer is simple. A character is simply the diagonal sum of the elements. If here these are three matrices, maybe they may be reducible or irreducible and so on. But if we just go for their diagonal sum, this has got a diagonal sum of 3, this has got a sum of 0, this has got sum of -1 plus 1, that is 0 and -1. So the characters are 3, 0 and -1 respectively in these situations. So we must clearly understand that a character is nothing but it is the sum of the diagonal element of any reducible or irreducible representations. Now, if you have got this, let us again look at what we call as a character table. So, on one side you have point group, other side you have notations for irreducible representations. From where they have come, we will discuss them. This is a very important thing. These are symmetry elimination operations, and the 1, 1, -1 and so on, they define the characters. The fourth and fifth column that gives the basis function x, y, z, rx, ry, rz and the binary products that we'll understand or we'll try to understand in the part 2 of how to understand the character table. Now, to construct a character table, what we generally know, the point group of the molecule, like for example C2V for water, and what we do not know, of course, the number of irreducible representations, their dimensions and their characters. These things are not known to us. So there are only two things that are known to us: a molecule with a point group and the symmetry properties of that. And to know this, what is required? Matrix representation for every element of that point group. It's decomposed into smaller dimensions to obtain its corresponding irreducible representations, and then we have to find out their characters. And is it going to be cumbersome? Is it going to be very problematic? Is it going to be very tedious? Yes, of course. Yes, of course. If you don't have any adequate knowledge of matrix algebra, this is going to be very complicated indeed. But then, with dear students, the great orthogonality theorem is there. We have fortunately the great orthogonality theorem, which assists us to draw or to make a character table without actually constructing the matrices. And remember the great orthogonality theorem that we have discussed earlier, but it was, the properties of irreducible representation. It was referred as the properties of irreducible representation. Here we are referring as the great orthogonality theorem, though both of them are the same things. Well, now what? If we know this, we can be in as comfort as the man in this sketch. So, the great orthogonality theorem, and let's try to understand what are its components and how it is used without actually devising, constructing matrices, decomposing them and all of that. So there are 5 important points, and let's start one by one. Point number 1, the sum of the squares of the dimensions of irreducible representation of a point group is equal to H. H is the total number of symmetry elements in operation that a particular molecule does have. So the square of the dimensions is equal to the order of group. This is rule number 1. If L1, L2, L3, etc. are the dimensions, then the square and the summation should be equal to the order of group. This is the rule number 1. Rule number 2 states that the sum of the squares of the characters of irreducible representations of a group is also equal to H. So chi I square is equal to H. Chi1 square plus chi2 square plus chi3 square plus and so on is equal to H. Chi1, chi2, chi3, etc. are the characters of irreducible representations. This is rule number 2. This is about the characters. Rule number 3, the most important component of the great orthogonality theorem is the vectors whose components are the characters of two different irreducible representations are orthogonal. That is chi I r into chi j r, and their summation over entire operation r has to be equal to 0. So where the character of ith irreducible representation is chi I r